There are certain characteristics of the thermodynamic properties, the thing that we actually defined in the previous lecture. So let's see what are the features of those properties. First characteristic is that the properties are independent from past history. What do you mean by past history? So let us consider we have some graph plotted of between your pressure and volume, and this some variation is being shown. So the property at point 1 is independent of the property initially found, and the property at point 2 is independent of point 1, and property at point 3 is independent of what was property at point 2 and what was property at point 1. So they are independent of each other, so they don't depend on the history of that. So point 1 value means here the pressure will be P1, volume will be V1, temperature will be T1, entropy will be S1, and so on. So whatever the property at this particular point will be the values of that particular point itself. It doesn't depend on what was there in the previous case, and so on. So that is what the meaning of this first line says, that the properties are independent from past history. Remember this statement, because these type of questions generally are put up in your assertion region questions, and they try to confuse you with the statements. So first characteristic is that the properties are independent from past history. It has nothing to do with the previous results. Properties are independent from path imply that the properties are point functions. It means that whichever path you follow, it doesn't depend upon the path that you follow. So let's say we have a state 1, and at that state 1 we have some pressure value as P1, volume value as V1, and we have some another state that is 2, and here we have some pressure value as P2 and this volume value as V2. Okay, so whether you go by this white path or whether you go by this green path doesn't matter. The value at point 1 will be this itself, and the value at point 2 will be this itself. This is not going to change. It is not happening that if you are going by this white path and the value of that point 2 will change, and if you go by this green path, the value it will have some other different value. No, the point 1 will be having a definite value at this particular point itself. Similarly, point 2 will be having some values at this particular point itself. Fine. Now the third characteristic is that the properties are your exact differentials. Now let's see what do you mean by exact and non-exact differentials. So exact differential and non-exact differential, if you find the definition in your mathematics point of view, you will get that some used to study some dou m by dou y is equal to dou n by dou x. This sort of definition was given to us in mathematics, but this is not quite applicable here. This is of course applicable, but this is not quite relevant in this particular point of time. So from thermodynamics point of view, or from engineering analysis, what is important is, say if you are integrating anything, let's say we have integrating dx, okay, from 1 to 2. So we know that integration of dx is x. Now if you put the limits, it will be of course x2 minus x1. So if you integrate dp, so it will give you P2 minus P1. So here, since we can integrate this dx with respect to x, and then if you substitute the limits, we will get some difference. Okay, so if you are getting this sort of relation, then only we will say that this differential is an exact differential. On the other hand, if you are differentiating something like this, maybe with work or heat, so in that case, if you are integrating it, so in that case you cannot write the integration of d cut w from 1 to 2 as w2 minus w1. No, if you are writing it w2 minus w1, it means that you are making this term exact, which is not possible. So you should remember that heat and work are your inexact or non-exact differentials. They cannot be differentiated exactly. Okay, so here we can show that the difference has to be there always if you are differentiating any parameter in case of exact differential, and in case of non-exact differential you should not be able to integrate, rather you should not be able to put the limits as such. So if you are integrating this d cut w, it will be simply written as some work done which is happening from 1 to 2, and you can show this with the symbol called d cut, or another symbol you can use as del. Same thing you can apply for heat as well, that is d cut q or del q. Okay, so these were the things that were important from the point of your characteristics of thermodynamics point of view. See you in the next lecture. Till then, bye.